Hi guys, we are jumping right into chapter 9, exploring quadratic functions. So you've seen those a bit. They're the parabolas that either open up or down. We're going to learn how to graph them in different ways and then eventually how to solve quadratic functions. So let's take a look at our general understanding for this topic. A quadratic function is a type of nonlinear, so it's not a line, that models certain situations where the rate of change is not constant. So those are a couple terms that you need to understand go with quadratic functions. The graph of a quadratic function is a symmetric curve with the highest point corresponding to a maximum or minimum value. So we're going to take a look at those together so it makes a little more sense with that vocabulary. The quadratic function in standard form is y equals ax squared plus bx plus c. So we're already familiar with that form. We've been factoring it for the last few weeks. Sometimes you will see f of x instead of y. It means the same thing, just means that it's a function. And quadratics are a function because they pass the vertical line test. So let's see. A and b are coefficients. And a cannot be 0, because if a is 0, anything times a is, or anything times 0 is 0, so that would go away. And I'd end up with bx plus c. Well, since x's power is 1, I end up with a linear equation, which means I would have a line, because the value is 1. So you want to make sure that if a is 0, then that cancels out this whole quadratic function stuff. So you would have a line that looks like bx plus c. And c in the function is your constant term. Okay? There's a couple different looks for these graphs. You're going to have a positive quadratic function, so it's going to open up, and that one's positive. And you can also have a negative quadratic function. So this is negative and opens down. We'll take a look at what makes them open up or down as we go through today's lecture. Let's see. The shape that this makes, this is known as a parabola in fancy math words. So it's either a smiley face, happy face, or it's a frown, sad face when it opens down. Let's take a look at what happens when we change the value of a. When we are looking at what is called the parent function, that's the original base, nothing added, nothing changed function. It's called the parent function. The value of a is 1. So we want to see what happens when we change that value. So as you can see, we're going to graph some quadratic functions. This one has a equals positive 3. This one has a equals 5. So we are making a bigger than the parent function, and we want to see what happens. So we're going to start by graphing using a table. We will learn how to graph without a table later. So if I substitute in these values for x and find that y is 12, negative 1 squared is 1 times 3, so y is going to be 3. 0 times anything gets us to 0. 1 squared is 1 times 3 is 3. And 2, when I substitute in 2, 2 squared is 4 times 3, and I'm back to 12. As you can see, we're symmetric about its, what we're going to find is the axis of symmetry here. So 12, 3, 0, 3, 12. You're going to find that in every single quadratic formula that you have. Let's take a look at getting some charts here first. If a is 5, I substitute in 5 squared is 25 times 5. If a is 5, I'm substituting in negative 2. So negative 2 squared is 4 times 5 is 20. Negative 1 squared is 1 times 5 is 5. 0, when I substitute it in times anything, is 0. And then I automatically know I have a 5 and a 20 because I'm symmetric about that axis point. So let's graph those couple. If we are looking at 3x squared, and we graph points negative 2, and obviously x is double way up here, so my y is way up off the chart. Negative 1, 1, 2, 3. We can graph on that one. 0, 0. That one's that one. 1, 3, 1, 1, 2, 3. And again, we're going to have 2 and y somewhere way up off the charts. So we're just going to sketch this portion of it. Now, parabolas are always rounded, so no sharp points at that. That's 3x squared. No sharp points at the curve. Okay, it's a curve here, so make sure it looks like a curve when you plot those points. And then we have our 5x squared. So let's graph these points. -2, 20, again, it's going to be off the charts. -1, 1, 2, 3, 4, 5. We have 0, 0, 1, 1, 2, 3, 4, 5. And we have 2 and 20 way up here. So what we can see, though, is when I then connect these with a rounded point at the bottom, 5x squared, is that my graph gets skinnier and skinnier. What happens when A grows or gets bigger than 1, it's like a rubber band. So if I'm originally just hanging out, as A gets bigger, my rubber band starts to stretch upward. So its shape will get skinnier and skinnier as my A gets bigger and bigger. Okay? So let's see what happens when we get a smaller A. So now A is less than 1. So we have A equals 1/2 in this case, and A equals 1/4. And 1/4 is half of 1/2. So let's see what happens with those. So as A gets smaller, let's substitute in our point values for x. -2 squared is 4. 4 times 1/2 is 2. -1 squared is 1 times 1/2 is 1/2. So I'm going to call that 0.5. 0 times anything is going to get me back to 0. 1 squared, I end up back at 0.5. And 2 we know is already 2 because it's symmetric. Let's do 1/4 real quick. If we drop in -2 squared, that's 4 times 1/4. That means we're going to have a 1. -1 squared times 1/4 is 1/4, which is 0.25 when we're graphing. 0 times anything, when I substitute that in, it'll be 0. I know I'm symmetric, so I know this is automatically going to be symmetric around 0. So if I plot those points on my graph, let's go ahead and do that. -2 and 2, 1, 2 is right there. -1 and 1/2, somewhere in there. 0, 0. I have 1 and 1/2, and I know I'm in the same distance away from there, so I end up with a graph that looks like something like that. Y equals 1/2 x squared. So as you can already see, as we get less than 1, the smaller and smaller that number that we get for A, we're going to get fatter and fatter. So our 1/4 x squared should be even wider than our 1/2 x squared. So -2 and 1. -1 and 1/4. 0, 0. Then we know we're symmetric, so 1 and 1/4, and 2 and 1. So as we predicted, this one is going to be even wider than the other. Oops, that's 1/4 x squared. So as the number gets smaller, my graph gets wider and wider. We should note, though, that this continues on forever. So my x's are really, I'm getting more and more negative as I'm getting more and more positive. So do my x's ever end? No, because my arrows, this will go on infinitely. So my domain is going to cover all my x values because I started here at 0, and I will get every negative x that I can get, and I will get every positive x that I'm going to get. So I know my domain for these quadratic functions are all real numbers, or in math shorthand, all real numbers. So if I take a look at the range of all these positive values, the range are your possible y values, so I don't have any possible x values, or negative values for my y. This y is my up and down. And y will start to keep going up and up and up and up. Y in these cases of these quadratics keeps going and going and going. So my range is going to be y is greater than or equal to 0. Any values 1 million, eventually these will get up to 1 million. And further. Alright, so let's just make some notes about what happens when we are changing the a value or the leading coefficient of our quadratic function. So as a is positive, I know my parabola opens up. So you can think positive, I'm happy, I have a smile. If my a is negative, then the parabola opens down. That's a frown. If I am negative, I'm grouchy, I am frowning. As a gets bigger than 1, so as a went from 3 to 5, we see that it gets skinnier. So we want to use proper math words for that. That is called stretches. Because my, stretch, if I can spell right. Because my rubber band, you think about a rubber band stretching higher and higher for my A, stretches up, I get skinnier and skinnier. So this is a stretch. So you're going to use that word right there, stretch. And the opposite is true when my A gets smaller and smaller. Smaller, it gets wider or fatter. As I shrink and smoosh it down, it's going, all that blubber has to go somewhere, so it's going to smoosh itself out and get wider and wider. So the math term for that is shrink. Gets wider because it's shrinking down, but it's widening out. So watch not getting those backwards. So I shrink down and get wider as I shrink down. Alright, let's look at when we have a change in the constant, or the c value. So again, if I have f of x is equal to x squared, there's no changes to x squared, so that's called the parent function. There's no bells or whistles, no add-ons, it's just x squared. So that's my parent function, and I want to see if I add a constant, or if I subtract a constant. Here's another subtracting a constant. What happens to the function? So we are going to start by graphing these, and we're going to use a table to do the graphing. If I start with negative 2 squared, that's 4, plus 3, that is 7. Negative 1 squared is 1, plus 3, that's 4. 0 squared is 0, plus 3, that's 3. 1, I'm back to 1, so I know it should be the same, and I should end up 4 and 7. So let's take a look at graphing these. Negative 2, 7. Negative 2, 1, 2, 3, 4, 5, 6, 7. Negative 2 sevens right there. Negative 1, 1, 2, 3, 4. I'm at 0, 1, 2, 3. We should be able to see the difference already. When we were graphing our other graphs, our curvy part was right here at the 0 when I didn't have any c terms. So if I look and see, I shifted it up 3 by adding a constant of 3. So I'm going to finish graphing these symmetrically through here, making sure it's curved at the bottom. That's y equals x squared plus 3. What if I shift it down 4? Negative 2 squared is 4, minus 4 is 0. Negative 1 squared is 1, minus 4 is a negative 3. 0 minus 4 is a negative 4. 1, I'm back to 1, so if that's a negative 3 up there, this should be a negative 3 down here. If I'm back to 2, if that's a 0, this one should be a 0. So let's graph those. I'm at negative 2, 0. So let's go right there. Negative 1, 1, 2, 3. 0, all the way down here at 1, 2, 3, 4. Negative 4. Where are we at? 1, then 2, 3, and 2, 0. So as you can see, since I subtracted 4 from my starting initial parent point at 0, then I shifted it down. So the c term is your y-intercept. Y equals x squared minus 5. And the last one we need to graph is y squared. Oh, that's not minus 5, that's minus 4. Sorry. Now we want to graph minus 5. So negative 2 squared is 4, minus 5 is negative 1. Negative 1 squared is 1, minus 5 is negative 4. 0 minus 5 is negative 5, so there's our vertex. 1 minus 4 is negative 4, and negative 1. So negative 2 and negative 1. Negative 1, 1, 2, 3, 4. 0, negative 5. 1, negative 4. And 2, negative 1. So we can see that our shifting down one extra spot is going to shift slightly lower. Y equals negative x equals x squared minus 5. So what we can pull from that is that the changing the constant, if I add c, that shifts. That's a word you're going to use when you're describing up. Or if I subtract c, I'm going to shift down. What we should be able to notice too is that in every single one of these quadratics, we have what's called an axis of symmetry. It's the line about which both sides of the parabola are the equal distance away. So it makes this shape be a mirror image or a reflection across the axis of symmetry. So your axis of symmetry in all these quadratic functions is the line that divides the parabola into two congruent. Remember, congruent means fancy word for same halves. So I end up with two sides. So if I have a parabola, I can chop every single parabola quadratic function that I have in half with the axis of symmetry. It goes right through the middle of my parabola. And what happens is that parabola then, not only does it chop it in half, it tells me what's known as the vertex. So this is my vertex. It's the point where it intersects your quadratic function. So your vertex is the highest or maximum or lowest, also known as minimum, point on the axis of symmetry. And the lowest or highest will depend on whether you have a negative a term or a positive, whether it opens up with a positive a or if it opens down with a negative a. So if the parabola is opening up, the vertex is, so if I'm following the line of the quadratic function, I go down to a minimum point and then I turn around and start getting higher again. So it is the minimum vertex. So this is my vertex right here. Exact point of lowest on the quadratic function. If I open down, so I have a negative a term and I'm tootling along following my quadratic function, I see I go up to a maximum value for my y, and then I start coming back down. So this is my maximum point. This is my minimum point. Okay, so that's all the language of terminology. Let's play with a few of these. Figure out what we got going on. Oh, but first we need to remind ourselves what domain and range. So we talked a little bit about this already on the first page. The domain is the set of all possible x values in all quadratics. If you take a look at it, whether it's a downward facing, opening downward or opening up, my x's keep going and going and get wider and wider and wider. Slowly, but eventually you get wider and wider, 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 wider. So your domain is always going to be your all real numbers. So it's how far left or go, how far left or right the graph goes. And it will always be all real numbers. That's as always. The range is your set of all possible y values. It's how high or low the graph will go. So depending on whether it's opening up or down, it will always be a y is less than or equal to something, or y is greater than or equal to something, depending on which direction your parabola is opening. So let's take a look. So identify the axis of symmetry, so we want to look at the AOS. The vertex, whether it's minimum or maximum vertex, and we want to take a look at the domain and range. So for each of these, we're going to start by indicating that we are looking for axis of symmetry. We're looking for the vertex. Remember, the vertex is the maximum or minimum point on the parabola, the domain, and the range. So my axis of symmetry is the line that chops my parabola in half. It is the line of reflection for my parabola. And I will always have an axis of symmetry that is an x equals. It's always going to be a vertical line, so it's x equals, and then whatever point it crosses through. So in this case, if I look at where this line is crossing the x-axis, 1, 2, x is equal to 2. The vertex is the point, either the highest or lowest point where the axis of symmetry crosses your quadratic function. So if I'm looking at this point right here, it's 1, 2, and up 1, so that's the vertex of 2, 1. So I need to indicate whether it's minimum or maximum. If I'm tooling falling down, I go to a minimum point, and then I turn around and come back up. So this is a minimum vertex at 2, 1. It's always a point, so you need your xy coordinate. Domain, we know, is all the x values. This is going to keep getting fatter and fatter and fatter, fatter and fatter over time, and it's going to cover all real numbers. My y, or my range, is where my y's are going to be. So if I'm looking at this parabola, there are no y's below 2. It never touches any of these y values here. It always goes up, starting at 2 or above. So y, your domain, or your range, is going to be your y is greater than or equal to starting at 1. Okay, let's try this one. We've got an axis of symmetry. That's what we're looking for. We need a vertex, we need a domain, and we need a range. My axis of symmetry chops my parabola in half. It is the line of reflection. The vertex is the maximum or minimum point, so I'm going to go ahead and label that 1, 2, 2, 1. This vertex is also 2, 1. But we see it's opening down. My line of symmetry still crosses my x-axis at 2, so it's x equals 2. I tootle along left to right. I'm reading it. I go up to a maximum number, and then I start coming back down. So this is a maximum vertex at 2, 1. Domain is all real numbers. And my range for y's, my range is my y. I don't have anything above 1, but I have a bunch of y's, -5, -6, -6, all the way keep going down. So my y's are going to be less than or equal to 1. Let's do this one. So this one's a little harder to see, but this is my line of symmetry, or my axis of symmetry. I know it's crossing at -3, so my axis of symmetry is x equals -3. My vertex is the highest or lowest point, so I'm going to go document what this point is. -3, 1, 2, 3, 4, 5, -5. It goes down and then hits a minimum and comes back up. So it's a minimum vertex at -3, -5. I need my domain. Will always be all real numbers. And my range is going to be y. And I take a look, well, everything greater than that lowest y, so greater than or equal to -5. Okay, one more to do together. We've got our axis of symmetry right there. That point or vertex is at 0, 1, 2, 3, 4, 0, negative 4. My axis of symmetry is where it crosses the x-axis at x equals 0. My vertex is going down to a minimum, coming back up, so it's a minimum at 0, negative 4. My domain is all real numbers, and my range is y equals. And what you're going to find is that your range is picked up right where your vertex point is anyway. So I know it's going to be negative 4. And I just have to decide if it's above or below negative 4. Those are negative 4. Okay, so pause the video here, and then you try these next graphs as well as these last problems down here on the bottom. Come back and check your answers. Okay, that is what you should have gotten. You should pause your videos, check. If you didn't get them, make sure you jot some notes down or try again and then come in with questions. The rest of your homework for tonight is to do the next page. So your next page is graphing calculator exploration. So you need your graphing calculator. You need to graph all the following functions on your calculator and then sketch them. So I don't want perfectly drawn graph papers. I want realistic. I should put a x-axis in and a y-axis in, and then reasonable graphs, representations of what you got on your calculator. And I will see you in the morning.